Okay, so we're talking about troubleshooting EIGRP. All right, so this is going to be, when it's not working right, what do you do? Okay, so the thing to remember, and this is important, is one of the first things that it does is it has to establish a neighbor adjacency to work, right? So if it can't establish a neighbor adjacency, nothing else is going to function. So one of the first things you do is make sure there's an adjacency. One of the ways how that process starts is by sending hello packets to the appropriate multicast address. And of course, how do you trigger that? By getting interfaces to participate with EIGRP. And with IPv4, we're going to use the network command. Okay, so in this example, this /24 network command is going to it's going to turn on EIGRP on any interface that has an IP address from 10.110 to 10.11255, right? Because this /24 mask establishes that range of IPs. Okay. This is a /32 mask, which means it has to match an interface that's 10.1.165 exactly. Or we can do this network command, which is essentially like similar to a default route, /0. All interfaces are going to be participating. Okay. So if you have a bad network command, this can make adjacencies not work. So this is one of the first things that you're going to look for if EIGRP isn't working. Okay, you probably won't look at the network command as like the very first thing. You're probably going to do a show IP EIGRP neighbors command. Okay, and that's going to get you this output. So that first column marked as an H, the H means handle. And that's just an internal number that identifies a neighbor. Neighbor 0 and neighbor 1, neighbor 2, neighbor 3, etc. Okay. Then we have the IPv4 neighbor interface that sent us the hello. This is our local interface that we use to reach the neighbor. This is the hold time in seconds. If it reaches 0, then we'll consider the neighbor down. Okay. The uptime, how long that neighbor has been a neighbor. So longer is better as far as stability goes. This is the smooth round trip time. Smooth as an average. So the time it takes to get an acknowledge packet after sending a message to the neighbor. Okay. And then we have the retransmission timeout. This is how long we're going to wait in milliseconds before retransmitting something to the neighbor. And this is by default 6 times the smooth round trip time. Okay. 0, well, actually, over here, the smooth round trip time, if that was to say 0, then that means we have never gotten an acknowledgement from that neighbor. So that wouldn't be good. Okay. Here is the number of packets that are queued to be sent to the neighbor. And of course, that should always be 0 in an ideal world. Okay. The last received sequence number, and this ensures that, the EIGRP packets have a sequence number similar to like how TCP segments have sequence numbers. Okay. And so this helps us to make sure that as we're talking to the neighbor, we're only kind of taking new information. Okay. So this is one of the first things that you're going to look at when you're troubleshooting problems. Is that neighbor that we're expecting there, right? Do we have a neighbor relationship? The interface has to be up, right? I mean, and this slide here actually is a good list of things to check when you're troubleshooting. Don't just try to shoot from the hip and just try to think of things to check when something doesn't go wrong. Have a checklist. Do like the pilots do before takeoff. They've got a checklist that they go down, and they've got the checklist memorized, but they still physically go down the checklist because if they just space it and forget one thing, well, that could have been the thing that you needed to check. Okay. The autonomous system numbers must match. Network statements have to be correct so that the right interfaces are participating, right? The K values have to match. Though you can change those, but any K values that you change on an EIGRP router have to be mirrored on all of the routers in the EIGRP domain, okay? Passive interfaces are not going to send hellos. If you don't send hellos, you're not going to form an adjacency. That may be desired, but maybe not. If there's an adjacency that is missing, make sure it's not a passive interface. The subnets have to be the same. If you have an interface that's misconfigured, well, the hello from that interface will be ignored if it doesn't match the receiving interface's subnet. Okay. Authentication, all right, kind of self-explanatory. If you don't have the key, don't be surprised when the door won't open. Okay? If you don't have authentication properly configured, don't be surprised when the hellos and stuff are ignored. ACLs, don't block the multicast address that EIGRP listens to. Now, timers don't have to match, strictly speaking, okay? But if they are misconfigured or way out of whack, that could cause problems, all right? We'll look at some of these in a little bit more detail, but again, just remember, this is a good checklist to verify that everything is correct when you're actually troubleshooting problems, all right? So this first one, interface has to be up, okay? One good command is show CDP neighbor, all right? This will verify a physical connection. Okay, and this works even if the interface is up down. CDP is a layer 2 protocol. So if layer 3 is down but layer 2 is up, CDP will still work. So and of course, we're like, wait, when does that happen? Well, so no shut, right? It's not shut down. But say it's a router interface that does not have an IP address on it. It'll be up at layer 2, but it will not be up at layer 3. It needs an IP address. Okay? Well, CDP is a layer 2 protocol. We send CDP frames between the neighbors. So you can do show CDP neighbor, and you can actually have a neighbor at layer 2, but have nothing happening at layer 3. So that's kind of nice. Okay? So more detail. It's
Sorry. So going back to that last slide. So basically CDP neighbor is going to give you the default information, the device, the MAC address, but it's not going to give you an IP address then at that point.
Well, if that's a good question. Now off the top of my head, I'm trying to remember if it does tell you IP address.
Well, if it doesn't have one.
Yeah. I mean, if it doesn't have one, then yeah, there won't be. And you can also do a show IP interface brief, and you'll see the up down. But yeah, I mean, you'll see all sorts of stuff with CDP, including the host name, the version of the iOS that's running on the router. It actually can give you, especially if you specify a specific neighbor and add the word detail to it, you can really drill down a lot. But yeah, if there's no IP address on the interface, then yeah, it won't be able to give you any IPv4 or any IP information.
Yeah, and that would be dependent on that device actually supporting CDP or having it enabled.
Yes, that's true. Because if CDP is disabled, then it's not going to send or receive CDP frames, and it's not going to exchange information, because at layer 2, when two CDP neighbors are communicating, they're actually exchanging information with layer 2 frames. So normally, standard procedure is, because CDP does share such detailed information, host name, the type of device, like hardware-wise, the version of the iOS, that information is kind of dangerous from a security perspective. So normally what you do is network infrastructure devices a lot of times we'll have CDP enabled, right? But at the network edge, where it's kind of like not a protected environment any longer, we'll shut CDP off unless we need it for a specific purpose, like a VoIP phone or something like that.
And LLDP would be just the counterpart. That's the global.
Yep. So LLDP, is the open standard version of CDP. So like if you're on Windows and it says, hey, do you want your Windows computer to be discoverable on the network? What it's actually asking you is, do you want me to turn on LLDP or turn it off? Or if you want to say, you explore the network neighborhood. Well, it's doing that via LLDP. And of course, Cisco routers are compatible with both. CDP is on by default. LLDP is off. So you'd have to turn on, LLDP run versus, no CDP run to turn CDP off. But the commands for LLDP and CDP are almost identical, with the exception of LLDP. You do have a receive and transmit. Whereas CDP is just on. If you're going to receive, you're going to transmit with CDP.
Right. Okay. Thank you.
Mm-hmm. Okay. Interface has got to be up. Show IP interface brief. Up. We talked about CDP neighbor. The autonomous system numbers have to match. Most EIGRP show commands will show you what it is. Okay. So you can use the spot the difference to compare the autonomous system numbers, right? So here we have show IP protocols, and we see AS100. Issue the command on the other router, see what it says. Okay. We can also debug EIGRP packets. In this example, come on, there we go. We can see that apparently we are not receiving any hellos, but we're ignoring them because the autonomous system number is different, right? We can't actually tell that from this output though. Incorrect network statement. If you do a show EIGRP interfaces, this will tell you what interfaces are participating. Keep in mind this does not show passive interfaces. All right. So in this case we have two interfaces participating. Okay, gig 00 has no peer, and gig 10 does. Okay, if gig 00 happens to be a LAN interface, then this behavior would be expected. Okay, but if our documentation, yes, network documentation, indicates that there should be a peer there, then you're going to need to drill down a little further and see what the problem is. On the right, the pending routes column. This basically says, how many routes are pending to be sent to the neighbor. It should be 0, ideally. If that is non-zero, that could indicate a problem. Okay. The show IP protocols command will show us, essentially those network statements. In this case, they're both /32s. All right. Again, just a reminder, don't confuse the network statement with what networks are actually going to get advertised, because that's not what the network statement does. All right. The show run is one. This is a rare case where show run might be a good go-to command to verify the exact network command. Okay. K values, again, they must match. Each of these K numbers, these are 8-bit numbers. They're not binary. So by default, they're either 0 or 1, right? 1 and 3 are 1 and the others are 0. But they could be as high as 255. So you can imagine the crazy metrics that would generate. Okay, but they need to match on every router or you'll get a message that looks something like this. Passive interface. Well, the nice thing about those, we're going to reduce the amount of EIGRP traffic on a network. It's going to allow the associated network to be advertised. It also ensures or improves security because we're not going to form an adjacency in a direction that we shouldn't be forming adjacencies. Okay. But the downside is this could prevent us from forming adjacencies when we want them. So show IP protocols, we can see that there is a section that tells us about our passive interfaces. Okay. Now, in order for the adjacency to form, they have to be in the same subnet. Multiple commands to verify this. Okay. Essentially, just whatever you do to verify the actual IP address and subnet mask on two interfaces that are connected on two different routers. But notice here, a problem with dual neighbor information. This neighbor is not on a common subnet. So, that part right there, not on a common subnet, or not on common subnet, that kind of gives it away. These syslog messages that show up on your, screen, or if you're actually looking at logs or something, do tell you a lot of information. Okay. Authentication, again, self-explanatory. You set up authentication so that you will only form an adjacency with legitimate routers, and you'll only accept EIGRP packets from those routers. All right. The best way to troubleshoot this is to use the spot the difference approach. There's no command that really says, oh, the authentication failed due to a bad secret or a bad password. No, it just doesn't work, and it's your job to figure out that it's authentication is the problem. So you just have to know to kind of check that. So we do a show run interface. Okay. Include authorization. Now again, this is IPv4 because remember, for IPv6 EIGRP, none of this would be on the interface. It would be in the router configuration. But the nice thing is you just look at the router configuration and you'd see authentication right there without having to look at all the individual interfaces. Okay. And so show IP EIGRP interface detail. Okay. Include auth. This time it's a capital A. And keep in mind, these pipe commands and what it's looking for over here is case sensitive. So that's a little bit of a hassle here. Although you could just do auth, pipe, no spaces on either side, and then auth. And that would basically look for uppercase and lowercase. I think it'll accept regex too. You could do a, and then something like that. That's a bracket, not a brace. Square bracket. So the key string must match. It's got to be valid, right? So key 1 here. That string has to match. The key number doesn't necessarily have to match. But notice, it has to be valid. Debug can help. Again, it's so here the debug, actually I think I said that nothing will tell you that it's authentication unless you turn on debugs. So let me kind of clarify that. Debug can give you a lot of information. Okay, so in this case, one neighbor is not configured without authentication. Missing authentication. Not that the authentication is wrong, it's completely missing. Okay. Over here, we have invalid authentication. And you can see, like, the neighbor that it's from. We can see we ignored a packet, and it'll tell us why. And we can see it's an authentication issue. This missing tells you, because if you go to the neighbor, you won't see any authentication. That might kind of confuse you at first, but we can see right here, yeah, it's missing. ACLs can deny EIGRP packets, including the often forgotten implicit deny at the end. So the show IP interface will show you if there's an ACL applied to the interface. Okay. So we're going to do an include. Give me any line that starts with Ethernet with a capital E or the word list. Right? So Ethernet, list. Okay. So we can see here There is not an outgoing one, but there is an inbound one. Okay. If we do a show access list 100 command to take a look at the, what it's got in there. Oh, look, deny EIGRP any. Okay. Well, clearly that's going to cause a problem. That would be okay on like a LAN interface that it wasn't pointing toward a router, right? And maybe that would be a good thing to put on it too. Not only make it passive, but just deny EIGRP altogether. Okay. One thing to remember about these ACLs, though, is routers don't filter themselves. Okay. Routers are kind of narcissistic, and they assume that what they have to say is important. So any packet generated by that router, like an EIGRP packet, will not be filtered by outbound ACLs. Okay. So outbound ACLs cannot affect EIGRP packets, but inbound ACLs do, because even though the router thinks that what it has to say is important, it doesn't necessarily feel the same way about the neighboring router. The neighboring router talks a lot, and you can mute it with an ACL whenever you want. Okay. So back to the timers. Remember, they don't have to match. But if we're in a situation where we have a default timer of 5 and 15, R2 is at 20 and 60, well, R1's hold time of 15 seconds will expire before it receives a single hello from R2. That means the neighbor relationship will be formed. 15 seconds later, it'll be torn down. Show IP EIGRP interfaces detail. 5 and 15. Again, for IPv6, it'll be in named configuration mode. All right. Let's look at some more stuff. Bad or missing network command. Okay. Well, actually, let's do recap. Form a relationship. Exchange routing information. After that, exchange updates as needed. Routing information received will be put into the topology table. Best routes from there will be put in the routing table. If a route is not installed in the routing table, something would have happened at one of these steps. Okay? So remember, this information is only going to come from directly connected neighbors. So if you don't have a path, you can follow the path to figure out where that problem is, right? If R1 doesn't know about the route and its neighbor does, there's probably something wrong between those two neighbors. Okay? Again, I can't harp on it enough that these neighbor relationships are the foundation of how EIGRP works. No neighbors means no routes. Okay? Now, there's lots of reasons that a route might be missing from either the topology table or the routing table. Now, if it's missing from the topology table, then it's going to be missing from the routing table, okay, unless it learned the route from someplace else. So again, missing routes, check your network commands. Or was there a better source of information? That /24 route that you're looking at the routing table. Was it learned via a static route, right? Is there route filtering anywhere? So it's actually being taken out of the routing update. Do you have stub configured somewhere where the update is not being sent? Okay. Or maybe the wrong router was chosen as the stub. Is an interface shut down? Is there split horizon? Okay. Split horizon is where if you advertise to me a subnet, I am not going to advertise that I know how to get there back out of that same interface. That helps to prevent routing loops. Okay. We'll see an example of when that can cause a problem here in a second. So, show IP protocols. Begin routing for. Notice the capital R. So we'll start the output here. Okay. So there is our networks. We've got a couple /32s. Okay. compared to the interface. Now we can pretty much disregard the mask on the interface itself, okay? We just need to make sure that these IPs are kind of contained by those network commands, all right? And we can see that they do. That /24 there aligns with that /32 in the network command. So to get a route from the EIGRP topology table into the routing table, it has to be the most trusted source in routing news, okay? So one of the things that we're going to do is look at the administrative distance. Again, relative trustworthiness of a routing source. For EIGRP internal routes, the default is 90. For external routes, it's 170. When we talk about route redistribution and things like that, we will look more at, you know, what external routes are and what they're for and all this, okay? But if we learned about a route from some other source that has a better or lower administrative distance, right? We're talking getting a packet from A to B, so a lower distance is always better. Then that lower AD source wins, and it will not get, the EIGRP route won't get put into the routing table. So in this example, we can do a show IP EIGRP topology. So we're looking at the topology table, not the routing table. And there's our subnet, 10.1.34.0/24. We can see we learned via connected. If we look at the routing table, we can see that it's not there. Well, because we're only looking for EIGRP routes, okay? If we look at the routing table specifically for that prefix, that subnet, and not specify EIGRP, we can see, oh, it is in fact in the routing table. It's known via connected with a distance of 0, which makes sense, right? And an administrative distance of 0. And of course, metric is 0 too, because connected has a metric of 0. It's directly connected, okay? Here's a scenario. PC1 wants to get to that subnet. There's 2 ways to get there. Which path is better? Any ideas? This is a hard one. I'll give you an easy one. Which way should we go? We've got 2 choices here, OSPF or EIGRP. OSPF, exactly. It's faster. It's 10 gig versus 1 gig. It's got fewer hops, but which one is our routing protocols going to use? Are our routers going to use? Which one? Right? We know it should use OSPF, but which one will it use? EIGRP, right? Because the administrative distance of 90 is shorter, I guess shorter in a way, less than the OSPF administrative distance of 110, okay? One way of fixing that is maybe lowering the administrative distance in just for that route. That would be one way of doing it. Distribute list. So this is going to be applied to the EIGRP process as a whole, either inbound or outbound. So inbound would filter advertisements being received from a neighbor. Outbound would filter our own advertisements that we were sending to the neighbor. Okay, this is done in router configuration mode. Okay, I basically just said that. A distribute list can use ACLs, prefix lists, route maps. Again, when we talk about route redistribution and route filtering, we'll look at this in more detail. Okay, so when we're talking about routes not showing up, we have to ask ourselves, is there a distribute list? Is it applied to the correct interface in the correct direction? And is it correctly using, you know, whatever it's using, whether it be an ACL, prefix list, or route map? Are those correct? Okay. So if we look at the show IP protocols command, we can see if there's any route filters on the protocol. Okay. we can set up a default filter that will affect any interface, either incoming or outgoing. Okay. In this case, we can see no outgoing or incoming update filter list for all interfaces has been set. No default list. Okay. We can also see if specific ones have been applied to specific interfaces. So gig 10 has ACL 10 applied to it. Okay. If we do a show run, there's the command distribute list 10 in gigabit 10. Okay. Show access list, show IP prefix list, show route map. Those will help us determine if those have been done correctly. Okay. So in this case, if we weren't seeing the routes, we would, since we have an ACL there, we would do the show access list and see, maybe it's blocking the path that we are missing. Okay. Again, if you configure a stub, that's going to suppress some things from being advertised. And the whole idea of a stub is that's what you want. But if it's done incorrectly, that's a problem, right? So here we don't have any stubs configured. R1 loses connection to that prefix. And what is it going to do? It's going to send a query out. Okay. We can see here now R4 is connected to the cloud, so maybe there's another way there. But we can look at this topology, and it's clear that R3, this query isn't super necessary. Okay. If it was set up as a stub, then essentially what would happen is the query wouldn't be sent. Right? But configuring these stubs could be a problem. So, actually, let me see. Did I advance? Okay. So here we've got a couple stubs. And in this case, when that link goes down, we're not going to send a query. Okay. So this is great, but if we were to send a query here, say these weren't stubs, and this was a WAN connection that maybe had some bandwidth issues, we might end up with a stuck inactive situation perhaps, or maybe we have a hard time establishing a neighbor relationship. Okay. So remember, with a stub configuration, by default, the stub is going to advertise connected and summary routes. Any other route, like redistributed routes, static routes, will not be advertised by default. Or if it's set up as receive only, well, it's not going to advertise anything. Okay, so the stub configuration has to be set up properly. Like, for example, if R1 was configured as the stub, right, R4 would never learn about the stuff over here. Okay, so because R1 is not a stub network, you can draw a line through it between two routers. Okay, so this should be a stub and this should be a stub. One way in, right? One way out. Show IP protocols will remind you of where there are stubs in your network. Show IP EIGRP detail will, neighbors detail will also, right? Interface got to be up, not up, down. Okay, move on up. So the split horizon rule means routes learned inbound on an interface will not be advertised out of that same interface in order to prevent routing loops. Sometimes this can cause problems though. Okay, so let's look here. All right, so here we have a multi-point interface. Maybe it's a serial frame relay interface, or it's a multi-point GRE tunnel like with DMVPN setup. Okay. So we essentially have two logical tunnels. So keep in mind, this is a multi-point interface. So, say this is 10.1.1.1, and over here it's 10.1.1.2, 10.1.1.3. Notice they're all in the same, subnet. Let's just keep it easy. Say it's a /24, right? They're in the same subnet. These are going to the same IP address. Okay, it's a multi-point interface on the left there. Okay. So those are frame relay tunnels or GRE tunnels or whatever. So R2 is going to advertise this LAN over here, but R1 is not going to advertise that to R3 because it's going out the same interface that it came in on. It's a multi-point interface. All right. So kind of think of it like, okay, so this is one interface, one kind of link. Now that makes sense because let's say these were connected for the sake of argument. And R1 advertised that over here. So R3 can, thinks that it can get there from here. Okay. So essentially, because there's a loop here, if one of those goes down, R1 can think that it can still get there. Like, so for example, if this goes down, R1 would advertise here that R3 could get there. Okay. R3 goes over here. I'm trying to remember how this causes a loop, but my mind is blanking.
When you have a routing loop like that,
does
the original entry get overwritten by the new one, or they both exist with equal metrics?
Well, no, because in theory, as it gets advertised around, the metric is increasing, right? So still the best metric would be the one that got installed into the routing table. So the metric wouldn't be overridden per se. It would be like the new route that came back has a higher metric. So if you did get that advertisement from two different locations, in theory, you'd still use the one that the best metric would have. The problem comes in this scenario is when a link goes down, then it's like or we can also black hole traffic, right? So R1 or R3 advertises that it can get to that network there. If that goes down, R2 will try to send it there. It'll send it there, then it'll get sent here, and then R2's like, oh, I got this packet, I guess I'll send it here, and then it keeps on going because R2 thinks that it can get to this network by going that direction. Okay. In this topology, the problem here with split horizon is R3 has no knowledge of that. So what we could actually do is disable split horizon on this interface because this is a hub and spoke topology. These are not connected. There is no risk of a loop here because you can't make a loop. There's no connection. So we would just turn off split horizon because we don't need to worry about guarding against creating a loop like I just showed because there is no loop, right? If we do a show IP interface brief, pipe includes split, we can see split horizon is enabled on that tunnel interface. So if we go to the interface configuration mode, we say no IP split horizon, and then we can verify, oh, it's been turned off. Okay. We can also turn off split horizon for all of EIGRP. That might be a little bit more dangerous, but In this case, you're only turning it off for that one router, so it could be okay. All right. So far, the focus has been on neighbor relationships and routes. Now we're going to focus on troubleshooting, just miscellaneous issues. All right, so looking at the concept of feasible successors, remember the best route in the topology table is the one that has the lowest feasible distance, or metric. That's going to become the candidate that gets offered to the routing table. We call it a candidate because maybe the routing table gets that same prefix or route from a better source, such as a directly connected route, okay? So we end up, if it does get injected into the routing table, we call it the successor route, which is the best route, okay? And that is what is advertised to the neighbors. Because again, we're only going to advertise routes that are actually in our routing table. So if a route doesn't make it into the routing table, it's not getting advertised. We can look at the topology table to verify this information. Show IP EIGRP topology, okay? So here, we're just looking at the 172.16.32.192/29 subnet, okay? And we can see we have the exit interface, the next hop neighbor IP address. This is that neighbor's reported distance, and this is our feasible distance, right? If we were to use that route, it is feasible that that would be our distance. So that's our distance or metric, okay? The best metric of these routes becomes the successor or the best route. So that route then now becomes our measurement that we're going to measure against to see if the other routes will be backup routes, okay? And those other routes will be feasible successors if the reported distance of those neighbors is less than our feasible distance, okay? Hopefully you remember all of that from last week. So remember, this command is only going to show successors and feasible successors. That means no loops. It's not going to show anybody that might give us a loop, okay? Now in this example, we only have one successor, right? That one right there. If we were to add the all links keyword, we see a second route show up. And of course, we can't use that as a backup because it could be a loop. It may not be, but it could be. Okay, and that's because that reported distance is not less than our feasible distance. We can also see routes that have been redistributed into EIGRP. So this was a redistributed static route. All right. So remember when we talked about automatic summarization at a classful network boundary? So this /30, 172.17, that's class B, so the default mask is 16. So we say, okay, well, what /16 does that belong to? Well, it belongs to 172.17.0.0, right? Same thing with these. Class B /16/16. These will belong to the 172.16.0.0. So we've got the 16 network and the 17 network. That means, there's a classful network boundary. We've got the 172.16 classful on the left, 172.17 classful on the right. So when these routes get advertised and it crosses that boundary, we're not going to advertise each individual route. We're going to advertise the classful boundary. Okay. So what does that mean if you have a discontiguous network with auto summarization turned on? Okay, so we've got this 172.16.2.0/24 at the top. 172.16.3.0/30 on the left. 172.16.1.0. Okay, so all of these belong, well, those three will get advertised like that, right? But only if we have the no auto summary command, which is the default, nowadays. But if we have the auto summary command turned on, then what would happen with, all of those networks? They'd be advertised as the classful summary network. Well, fine. So who cares? All right, well, say this link goes down. This router wants to send a packet to, or a bunch of packets to 172.16.2.1. Okay. Well, it has two routes, and because those are summary routes, we could say maybe the metric is going to be the same on those, and if that's the case, we're going to load balance our packets like this. Well, half of our packets are going to get dropped. It's getting black holed. So this is why we don't want to use auto summarization with discontiguous networks, where the classful network is split. And that's also why automatic summarization was turned off, because most networks are not classfully designed where auto summarization would work. They would usually have a problem like this somewhere. So we use the show IP protocols command and limit it so that we can see, automatic summarization disabled. We are summarizing stuff though, but manually. Okay, so don't use auto summary. Use manual summarization if needed, and that way it'll be implemented on an interface by interface basis. Okay. If you are troubleshooting that, make sure you ask yourself, is route summarization on the correct interface? Is it set up for the correct autonomous system? Is the summary even correct? Right? So you can verify this using the show IP protocols command. All right. When you're summarizing these routes, obviously it's very important to get the routes right. So if not, you're going to advertise the wrong summary and start screwing stuff up. So if you don't have the summary correct, it could end up receiving packets for a route that does not fall within the summary, or that does fall within the summary, but that it really doesn't know how to actually reach. And the packet will be dropped because of that null zero route. That null zero route kind of helps protect us against some of this stuff, at least as far as having a packet floating around until the TTL drops to 0. Okay. Load balancing. So EIGRP by default will load balance equally across up to 4 paths. Okay, we can change that to equal a higher number of paths, up to 16. I don't think I've ever seen, it's rare to see equal paths even that go up to 4. We can also do unequal cost load balancing using the the variance command, which we saw before, which allows us to use our network much more efficiently. So if we set the variance of 2, that means we could use feasible successors whose metric is twice that of the successor. However, the feasibility condition must always be satisfied. We will never use any feasible successor if it doesn't, if it's a potential loop, no matter how high we set the variance. And then that load balance traffic will be sent proportional to the metrics. Okay. All right. Let's look at one of the trouble tickets for the chapter. All right, so the problem is users in 10.1.1.0 on the left complain that they can't communicate with stuff on the right in the 10.1.3.0 subnet. All right. You'll notice that the communication arrows here are depicted as 2 one-way arrows. We don't know which arrow actually is the problem, but it's important when you're troubleshooting this stuff to think unidirectionally, right? So if only one of those arrows has a problem, then the people on the left won't be able to communicate with the resources on the right, okay? And they won't know. Like, you can't just readily say, oh, it's traffic going from us to the resource, or from the resource back. It could be either way. Like, if you sent a ping, well, the echo request has to get there, and the echo reply has to come back. If there's a failure, oops, if there's a failure on either one of those, the ping is going to fail, but you don't really know which direction was causing the problem. Okay. So we've been hired to help, and we've got Miss Packet here who tells us that step 1 is always verify the problem. Generally, that means replicate the issue. So we're going to ping the 3 subnet from a host in the 1 subnet. So this is what it looks like. So from PC1 on the left, we're going to ping 10.1.1.1. I'm sorry, from PC1 at 10.1.1.1, we're going to ping 10.1.3.10. All right. So we go to the PC and we do that, and we can see, well, there's a problem. We had 0% loss, but, so that means each echo request got an echo reply, but the replies came from 10.1.1.1 saying destination host unreachable. So who's 10.1.1.1? It's our default gateway, which means we know that R1 cannot reach that subnet, but we also know that our PC can reach its default gateway. All right. So even though the ping didn't work, it told us some information. It told us we can reach our default gateway, but that the default gateway cannot reach that subnet. All right. So then we jump over to the default gateway. Okay. So let's go to R1 and let's see, does it have the route we're looking for? Show IP route. Well, if you'll notice, there are only connected routes. So we can hypothesize R1 is not learning any EIGRP routes from R2. If we issue a show IP protocols command, and we filter it out quite a bit just to make it simple, we can see, okay, AS 100, and it's supposed to be 100. We can see the network commands seem to be correct for the interfaces. Okay. What about neighbor relationships? No output. Remember, I said that's one of the first things you're going to look for. Okay. So if there's no output, well, are we sending hellos correctly? Let's check to see what interfaces are participating. Show IP EIGRP interfaces. All right, well, so far that looks correct. Those are sending and receiving hellos. Okay, the correct interfaces on R1. Let's see, are we connected at layer 2 at least to R2? Well, it actually looks like not bad. All right, R1 gig 10 connects with R2 gig 00 at layer 2 just fine. Okay, let's move over to R2. Let's do a show IP EIGRP interfaces. Well, gig 10 seems to be working. Okay. We can also see AS 100. That's correct. But gig 00 seems to be missing. Let's do a show IP interface brief. They're all up, even 00. With correct IPs, okay? Show run section router EIGRP. The network command is looking at the 21 subnet versus the 12 subnet. So we need to fix the network command. So we issue the no command, and then we enter the network command that should be there. We'll see that the neighbor adjacency will come up. So now let's go back over to R1 and do a show IP EIGRP neighbors command, and we see R1 now has a neighbor adjacency with R2. Okay. All right. Well, let's go back and let's try that ping again and verify that the problem was fixed. And we see that we essentially have the same result. Okay. So we still have a problem going on. R1, show IP route. Okay. Still no routes from R2. What about R2? Let's issue a show IP route there. What's the routing table there? R2 does not have the 10.3.0 subnet. Okay. So if we do show IP EIGRP neighbors for R2, we can see R2's only neighbor is R1, right, on the 12 subnet. Hold on, I gotta clean out the. There we go. Okay, on the 12 subnet, right? So R1 and R2. There's nothing over here. So on R3 now, show IP EIGRP interfaces, well, it does look like both interfaces are participating for R3. So what could the issue be? Autonomous System 10. Ruh-roh. So we need to fix the autonomous system number. Okay. So we just kill the entire EIGRP process. Probably do a show copy and then, so that you can paste. And then just paste all the necessary EIGRP commands back in. We see that the adjacency comes up. Now R2, do a show IP route. We can see that the 3 subnet is there. Hooray! If we go to R1, we can see that the 3 subnet is R1 as well. Okay, including other. We even have 2 EIGRP routes. Okay. All right, let's try pinging it. And it looks like it works. All right, that's it. There are a couple other trouble tickets. I'll let you read those on your own. Again, just walks you through troubleshooting steps. But that's basically it.